When you have a vector space V, it often happens that there are some subsets, U of V, which are also vector spaces in their own right, using the same addition as V, and the same scalar multiplication as V, and the same zero vector as V. In that situation, we say U is a subspace of V, because it's a subset which is also a vector space using the same operations. Not only is this very common, it's also very useful, for example, as a source of examples of vector spaces. So let's look at the definition. A subspace of a vector space V is a subset U of V which has the following three properties. Number one, it contains the zero vector. Number two, it's closed under addition. What that means is that if you have any two elements x and y in U, then their sum, x plus y, is also in U. Finally, U must be closed under scalar multiplication. That means for all scalars A and for all vectors x in U, the scalar multiplication A times x is in U. Let me say here what I mean by scalars. What that means is if V is a real vector space, then scalars are real numbers. And if V is a complex vector space, then the scalars are the complex numbers. So scalars just refers to numbers, real numbers or complex numbers, as appropriate. And there's a particular piece of notation which is always used for subspaces. We write U less than or equal to V to mean that U is a subspace of V. So that's supposed to look a bit like the subset symbol, except it should be different from the subset symbol because a subspace is more than just a subset. It must also obey those three rules. Let's take an example of a subspace. So we'll start off with the vector space R squared, space of all column vectors of height 2 with real number entries. And we'll look at the subset U of R squared, defined as follows. So U is all the vectors of the form x0 for x in the real numbers. Then U is a subspace of R squared. So to check that, I have to verify the three properties. Property 1 is that U must contain the zero vector. Well, for sure U contains the zero vector. It contains all vectors x0 for x, a real number. So in particular, it contains the vector 0, 0, which is the zero vector in R squared. So condition 1 is okay. Condition 2 is closure under addition. I have to take two elements of U and show that their sum is also in U. So those two elements of U must look like something 0 and something 0. Let's say x0 and y0. Well, if you add them, what you get is the vector x plus y 0, which is certainly an element of U. That means the second subspace condition is satisfied. So finally, let's look at the third subspace condition. I have to show that U is closed under scalar multiplication. So I pick an arbitrary element of U, which I know I can write as x0 for some real number x, and I pick a scalar. Now here we're talking about a real vector space, the real vector space R squared, so I should pick a real number scalar. Then if we look at the scalar multiple, A times x0, well, from the definition of scalar multiplication in R squared, that is ax, and then in the second place A times 0, which is 0 again, and that for sure is an element of U. We've passed all three tests, and therefore this thing is a subspace of U. A subspace of R squared, rather. So here are some more examples of subspaces of vector spaces. First of all, a generic example. If V is any vector space, then V is a subspace of V. That's true because V certainly contains the zero vector. It's certainly closed under addition. The whole point of addition is that if you add two vectors, you get another vector. Add two vectors in V, you get another vector in V. So for sure, V is closed under addition and scalar multiplication. Therefore, it's a subspace of itself. Also, the set just containing the zero vector in V is a subspace of V. It certainly contains the zero vector. It's closed under addition because the zero vector plus the zero vector is the zero vector again. And it's closed under scalar multiplication because if you multiply the zero vector by a scalar, you get the zero vector again. We proved that to be true in any vector space in our previous lecture. So there are two examples which work for any vector space V. Next, this set is a subspace of R squared. You could do a proof of that using precisely the same argument that we did on the last slide, only with the two coordinates flipped over. On the other hand, if you look at this set, which is the set of all height 2 column vectors with integer entries, that is not a subspace of R squared. So let's think why not. So if it's going to be a subspace, it must satisfy all three of those properties. Let's check them one by one. Oops. So property 1, does it contain the zero vector? Well, it does contain the zero vector. So I should give this thing a name. Let's call this thing U again. Okay, it contains the zero vector. Property 2, is it closed under scalar multiplication? Well, let's take two elements of U. So if A, B, and C, D are in U, that means that A and B and C and D are integers. So if we look at the sum, we get the vector A plus C, B plus D, and the first entry of that vector, A plus C, is an integer plus an integer, so that's an integer again. And similarly, B plus D is an integer plus an integer, so it's an integer again. So this really is in U. So we pass condition 2 as well. The problem comes with condition 3. U is not closed under scalar multiplication. For example, 1, 1 is in U. Root 2 is a legitimate scalar, an element of the real numbers. But root 2 times 1, 1 is not an element of U. That tells us that this subset U is not a subspace. To be a subspace, you must satisfy all three conditions, and here one of the conditions wasn't true. Let's look at another example. Curly F here is the set of all functions from the real numbers to the real numbers with the addition and scalar multiplication we defined 2 videos ago. We then let U, or curly U, be the set of all elements of F with the property that F at the input 1 is 0. Then that's a subspace of F. To prove that, we have to check all three conditions one by one and see that they're all true. The first condition is that U must contain the zero vector. But it does contain the zero vector. The zero vector in this case is the constant function which is always 0. So if you ask for the zero vector evaluated at 1, then you get 0, because the zero vector in this case is the constant function which is always 0. So certainly it's 0 or 1, because it's 0 everywhere. So it satisfies the condition to be in U. So 0 subscript F means the zero vector in F, which in this case is the constant function which is always 0. We've just established that is an element of our would-be subspace curly U. So we have passed test 1. Test 2 is closure under addition. So we must pick two elements f and g in U and show that f plus g is also in U. So if I want to know whether f plus g is in U, I need to know what f plus g does to 1. Well, f plus g of 1 is defined to be f of 1 plus g of 1, because that's how we define the addition of two functions in this vector space. The function f plus g is defined to be the function which sends a number x to f of x plus g of x. So in particular, f plus g of 1 will be f of 1 plus g of 1. And here, because f and g were in U, that's 0 plus 0, which is 0. That means f plus g satisfies the criterion to be in U. So the sum for any two elements of U is again in U, and U is closed under addition. Finally, let's pick a scalar A. So in our case, we've got a real vector space. A scalar is an element of the real numbers here. And let's let f be an element of curly U. Then I need to show that curly U is closed under scalar multiplication. So I need to show that A times f is in U. To do that, we have to investigate what happens when we evaluate at 1. Well, A times f of 1, again, by definition of scalar multiplication in f, that is A times f of 1, right? The real number A multiplied by the real number f of 1. But f of 1 is 0. So that's 0. That means A times f obeys the condition to be in U, and so U is closed under scalar multiplication. So U satisfies all three properties to be a subspace, and therefore it is a subspace. In some cases, we can actually visualize a subspace. I'm especially thinking here about r squared and r cubed, because we have a standard way of thinking of r squared as the plane, the set of all elements of the plane, so all elements in a particular fixed plane. And r cubed, we can think of it as three-dimensional space, because a vector with height 3 with real number entries specifies uniquely a point in three-dimensional space once you've chosen a zero vector, an origin. So we should be able to think of subspaces of r squared and r cubed geometrically, since we have this geometric interpretation of r squared as the plane and r cubed as three-dimensional space. So here's what happens when you think about subspaces. Every subspace of r squared or r cubed is either just the origin on its own, or a line through the origin. So in two-dimensional space, we typically illustrate two-dimensional space by drawing some axes like this, and then a subspace could be a line which must pass through the origin, since the subspace must contain the zero vector. So it might look something like this. A complete line like that would be a subspace of r squared. Or in the case of 3 dimensions, we might have a plane through the origin. So on the left of the picture there is an illustration of a plane through the origin, which is the black dot in the center. That will be a subspace because it contains the zero vector, that black dot. It's closed under scalar multiplication because what scalar multiplication does to vectors is it scales them. If we have concrete height 3 column vectors, then when you multiply by a scalar, it scales it. So it just changes its length, but not its, it doesn't rotate it in any way, it just scales it. And things in this plane, if you scale something in that plane, you get something else in that plane. And finally, it's closed under addition, because if you add two things in that plane, then you can imagine adding, let's try and draw this, a vector like this, and a vector like this. And of course the effect is you end up over here, so still in the plane. So a plane through the origin would be a subspace of r cubed, or a line through the origin, as in this other picture on the right there, which is supposed to show you a line through the origin in three-dimensional space, and that black dot is the origin, and you can see that it's closed under addition and scalar multiplication. If you add 2 points on that line, you get another point on that line. And if you scale a point on that line, you end up with another point on that line. So this can be helpful in getting some intuition for subspaces, because we have this for r squared and r cubed geometric interpretation for what subspaces look like. They look like lines through the origin, or planes through the origin, or the whole of r cubed, or just the zero vector.